Hello, welcome back to Math with Patrick and Quill. Today is October 13th, and we're solving problem 286 from the Daily Epsilon calendar. And X today should be 13 because the answer always matches today's date. So it looks like we have a system of three equations and three unknowns. And usually when you have the same amount of unknowns, like 3, and the same number of equations, you are primed and ready to solve for all three variables. Now, sometimes systems do or don't have solutions, but given that we kind of know that x is 13 already, we should find exactly one solution out of this system. There's two ways I'm thinking about it. We could actually convert this to a matrix and try to work through this as like a matrix problem. I think for starters, I just want to keep it with just algebra and equations, even though both strategies are basically the same. I'm just going to keep writing all my x's, y's, and z's. So the first thing that I'm trying to do here is essentially get two or maybe more of these equations talking to each other, as in with addition or subtraction, to try to eliminate one of my three variables. I'm noticing that these coefficients don't line up on any of these. They aren't equal on any of those. So I can't just simply add or subtract two of these equations with each other. I'd have to do something a bit more. Even if I added all three together, I'd still get a positive value for x, I get a negative value for y, and I would get a negative 1 for the coefficient in front of z. And so, here's an idea. If I take this middle equation and double everything, so I'll multiply the left side by 2, and I'll multiply the right side by 2. Now, if I add all three equations together, I will eliminate z. So I just noticed that, we can eliminate a variable doing this. So why not? Let's do that, and we'll eliminate the z variable from the equation, literally. Okay, so I'm going to add up all this stuff, and that should be equal to or balance to just adding up all these numbers on this side. And so I get 5 plus 4 plus 6x. So overall I have 15 x's. I have a minus 15 plus 2y, so that's minus 13y. I lined it up perfectly so the z's cancel. And then I do have, 12 plus the 2 is 14. This overall right here is a 9, and so I get 104. Cool. So I eliminated z, and actually, if we're just trying to directly solve for x first to get our solution today, I want to see if I can eliminate z a different way so that I have two equations with just x and y, and then I can eliminate y and then just get x. So let's do that. Let's figure out a different way to eliminate z. And I think let's get just the first two equations talking to each other. I'm going to multiply the second one by a negative 3 this time. So my first one is still the same. And then the reason why I'm multiplying by a negative 3 is, again, just to match the coefficients of the z's. And just for me, doing systems with addition just feels a little bit easier than with subtraction. But adding a negative is the same thing as just subtracting a positive. So I'm not really sure why it's easier to me to think of it in terms of addition. That's just a personal preference, I guess. But either way, I'm multiplying all of the terms by negative 3. So this will be a plus 12y, and then a minus 6x. Okay, cool. So adding these things together, I get negative 1x, or just negative x. I get positive 5y, or plus 5y. The z's cancel like I wanted to. And then adding those two numbers together, it's, again, just basically like subtraction. That's going to have a 2 here and a 2 there. There we go. And so from three equations and three unknowns, as long as you eliminate one of the variables, in this case z, two different ways, you are going to get two separate equations here. And then now we can just eliminate the y. It's not that friendly, honestly. The 13 and the 5 don't really line up. So I don't know. What do I want to do here? I guess I'll just keep using the elimination strategies, just because that's what I've already been doing. If I multiply both sides of this equation by 5, and then this equation by 13, we'll be fine. It's just, I don't really want to do that arithmetic, but I don't see a way out. Actually, I do. I'm just going to use my calculator. I don't want to have to worry about it. So multiplying the left side by 5, we get 5 times 15. That's 75. I could have done that in my head, but I chose not to. This right here is going to be a minus 65y, and then multiplying this by 5 is 520. Okay. Multiplying this one by 13, we get minus 13x plus 65y, and I guess this is the one that I didn't really want to do. 22 times 13, 286. Cool. And then now, this is equal to that, and so if I set up a new equation, I can put 75x minus 65y over here. I can put 520 here, and then this is equal to that. So I can put minus 13x plus 65y on the left, and then plus 286 on the right. Adding the numbers on the right side together, we do get 806. These y terms intentionally cancel, and so I'm just left with 62 x's. And then 806 divided by 62 does give me 13 for today. So that's our answer. Technically, we're all done. But I just want to know what y and z are supposed to be. So what we can do, armed with the information that x is 13, is we can go back to actually really any of our original equations and plug in that 13 to see what happens. But any of these would be a little bit hard to use right now, just because we still have two unknowns in each equation. So that's why kind of this intermediate step is a bit better to look at, specifically this one. I think it'd be really easy if I just plugged in a 13 right there. Kind of thinking like negative 13 plus 5y equals 22. I could add the 13 to the other side, so I get 5y equals 35. Cool. Y is now equal to 7. And I guess I should just double check that this works for my other equation, just for good measure. So supposedly, if I plug in a 13 here and a 7 here, I do get 104. And so I'm just calculating this again. 15 times 13 is 195. 13 times 7 is 91. Cool. And then once we do, 95 minus 91, we get the 4, and the 100 just kind of comes along for the ride. Cool. So now we know our x, now we know our y. We can plug in the 13 and the 7 into any of the equations to then solve for z. I'm going to pick the one that has z isolated and also has the smallest coefficients. So 2x, I think it was minus 4y plus z equals 8. And then here we can just kind of simplify. We can get this to be a negative 2. And that must mean that z is equal to 10. And then again, just to be confident in the work, we can substitute this back into either of the other two equations. Let's just pick the bottom one. It could have been the top one as well. 6 times 13 gives us 78. 2 times y was 7, is 14. We just learned that z should be 10, right? Hold on, I'm already forgetting. Yeah, so this is minus 50. And then we can check that indeed, if we add these together, we do get 92. Minus the 50 does get us back to 42. So I've double checked enough. I'm very confident, not certain, but very confident that if we plugged in the 13, the 7, and the 10 back into this top equation, we would also get 46. But just for the sake of time and not really needing to, I won't. I'll just trust that all of my other work works. So anyways, this is how you can solve for x when you have a system of 3 equations and 3 unknowns, and that 13 does match today's date. So I think we're all done. Thanks for coming along, and I'll see you tomorrow. Bye.